was going to try to get all this data put in here while you guys were working, but I ended up not doing that. So you all get to sit and watch me. Yay. If I were to tell you that see if I can multitask. The average for women was 64.25, and their standard deviation is 2.93. What are you guys getting for the standard deviation for the men? 3.123, that's what you should be getting. Oh boy, let's see if I got this in here. Alright, let's do a quick check here. Just remember, you can go to calc, one variable stats, bless you, and kind of double check. I already know ahead of time what the standard deviation is going to be. No. Oh, it's us? That's interesting. Hey, go ahead. Let's see where. Oh, so you can always go here first if you want to, kind of know ahead of time what you're going to get. And a lot of students are like, well, why should I do all this work when I've already got the answer? Because the work is what you learn. This doesn't teach you a damn thing. But at least you can check yourself. So in your list, real quick, just to kind of catch up to you guys, once you got that data in, if you go over and up, you always highlight the list. Can't put an entire list into one spot. So you tell it L2 is L1 minus 69.9 in this case. Then over and up. And now I want to square those so that I don't add up to be 0 all the time, right? Like we saw when we did it by hand on the board. So L3 is those things squared. So now these are all the squared distances from the mean. If I add them all up, divide by how many there are, and then take the square root, that's going to be exactly what I want the spread to be, how far they are on average away from the middle. So one way to add them up is first get the hell out of your list. Second, quit. See the quit right above mode? Second mode will quit. That gets you out of any freakiness you're in. If you don't like all that crap, you can clear the screen. Go to second stat to get the list. Math, and then 5 is sum, and I can sum up L3. That's what I want to add up right now. I want the sum of the squares of my x minus x bar. And you get this. Now take that divided by 18 minus 1. So that number there is what?
The variance.
Beautiful. It's called the variance. Right now, it doesn't mean a damn thing to us. It does have a purpose. It does have a reason. But right now, it's a middle step. It's like, I'm not done yet. But that's the variance. If I then take the square root, I kill all those squares I did before, and that's going to be the true spread of my data. Yeah?
Where'd you get it divided by 17? What's 17?
Oh, how many data points were there?
Oh, up here, okay.
18, and then n minus 1 will give me 17. Right? So if there's 18 data points,
Yes.
n minus 1 then will be 18 minus 1, 17. And why am I doing n minus 1? Because this is a sample.
Answer the last one.
Say again?
I say make the answer the last one more than 15 and be divided.
Yeah, so n here is 18, size of my sample, minus 1, 17.
What do you want us to write it, the answer 3 places after?
Yes, cool. And we're not done yet. So don't round this number at all. On your paper, you can round it a little bit, but don't round it. And here's the cool thing about this calculator. If I hit second squared to get square root symbol up there, right? What would really suck is to have to write, like, especially if it's longer than this, all those damn numbers in there. One of the coolest buttons on this calculator is the answer button. I was just about to lift this up so you guys can see, but that wouldn't really work. What if answer button down above the negative key? If you hit second negative key to have ANS show up, that's temporary memory. It always has the last number that showed up. So it's always changing, right? Right now it has 9.75 blah, blah, blah in it. So the square root of that is basically what that says. Enter. And there's that 3.123. So now ANS has 3.1227 blah, blah, blah in it if I had to do something else. So again, don't forget, when we did that stat calc, one variable stats, we saw right here, standard deviation 3.1227, that's exactly what we got, 3.123.
We're not loud it up on it.
Say again?
The answer, we're not loud it up, we just write all numbers.
Don't write it all. How far?
3 decimals.
At least 3, actually. Yeah. Normally 3 is good. If the standard deviation is really small, like 0.0001, going 3 places would make it 0. So you want to go even further if it's like a decimal standard deviation, way out there. You want to go capture a few of the actual numbers.
Can you tell what like the variance means towards the data? Like what it actually tells you?
One thing is the variance, this is getting a little ahead of ourselves, but one thing is the variance tells me is what's called an unbiased estimator. So when I'm trying, later in this class, we're going to try to see, have you guys, on the bottom of a screen when they're talking about presidential elections or something, they'll say like right now there's Bachman and there's Romney and there's Rick Perry and all that stuff in the Republicans, and they say, who would you vote for? Like 20% would vote for Perry and 18% would vote for Bachman, whatever. Right? She's actually slipping, but oh well. At the very bottom of the screen, you see that plus or minus 4 percentage points or something, right? So the variance is what I'd use if I want to get a feel for what the real standard deviation is. I can't use the standard deviation. I actually have to use the variance because it's a better estimator for what the whole population thing is.
Okay, because there was a question in 3.3 on the homework about using the variance, and I had no idea what it meant. So.
All right. I have to look at that one specifically, but they can't be getting too far ahead of themselves. How are we about this procedure? You will not be able to use your calculator Bible in the test. You'll have to know how to do it. You won't be able to use this handout on the test. You just have to know how to do this. Okay.
Square root, how we gonna use it, not use calculator.
How are we going to use it?
Yeah, then it have to become to square root.
Yeah, so there, well, I had it earlier. Oh, I wish this had a scroll, but too bad for us.
Well, if you not use calculator, how we gonna?
If you don't use the calculator,
Yeah, you say don't use calculator on the test.
Bible.
Oh.
the calculator Bible, yeah. Otherwise, it'd be really evil for me to say, look at all this cool stuff you can do, but I'm not going to let you do it. So, no, you can use the calculator. You just can't use the instructions. You have to know them. Okay, cool.
How do you get this page again?
Oh, go to Stat, Calc. If you want to calculate something with the data that you put in, you go to Calc, and there's all this other crap we're going to talk about later. We're going to have like 2 variable statistics at some point in this class, but right now I just put 1 variable in. Men's heights. That's the 1 variable. So I want to do 1 variable statistics. And again, just to show you real quick, it tells you a lot of stuff. It tells you the mean. It tells you sums of stuff. It tells you standard deviation. And if it's a population standard deviation, it gives you that. The N, it tells you the min, the median, all this kind of stuff. And some Q stuff that we don't maybe know yet. Right? Gives you more than you realize you needed to know. Okay. So any questions on that procedure? Okay, and again, just to remind you guys, I'm only going to make you go through that while we're in Chapter 3. Once we're out of Chapter 3, we're not going to do these tables for standard deviation anymore. We're just going to take it right out of the calculator. Okay. So the women's standard deviation was 2.93. The men's was 3.123. Are they very different in their spread? Not very. The women are just a little bit. What? What could you say? Well, they're shorter too from the averages.
They're closer to the average.
Yeah, the women's heights are just a little bit less spread out. They're a little bit tighter. They're a little closer together.
So the girls are more the same size.
Yeah, the girls are just slightly more uniform in height. Not really at all, but they're slightly more than the men anyway, right? And you would expect that because men, on average, can attain higher heights, but we can also be pretty damn short. So women in general don't get above a certain point, so they're going to have a little less variation. They have a little less that they can actually get to. It's a little less variation. So that actually makes sense. Cool. I might use that later. We'll see. So what I want to do right now is try to finish out section 3.3 and then see if we can get through at least a part of 3.4.
So we can do a z-test.
Don't need to. You don't need to do a z-test. You just have to calculate a z-score and compare it to empirical. Yeah, we're only going to know empirical rule by that point. We're about to talk about that. All right, guys. So one of the coolest things about standard deviation, and I desperately want you to understand this because, like I said, chapter 6 is the most important chapter in the book, and it's all built on the idea of standard deviation. Okay, that's a new one. I've never seen a pink one. Well, let me give you an example. And I always try to show examples from real life. And this isn't quite real life. Let's say there's a alternate universe where in Florida we have a lot of young people. So this is a graph of ages. So I went down and said, how old are you? How old are you? And I plotted a point. So I sort of made like a dot plot almost. And it ends up looking like this. A lot of young people and a lot of old people. Right? Kind of expected. So there's a lot of surfers and stuff, and there's a lot of retired people playing shuffleboard or whatever. Where would the average be, first off? Where would the average of this data be? So this is ages in Florida. So it's from like 0 to 110, let's say. Notice how nobody's under 10 down there, but so where did you say the average would be? Right in the middle. Even though there's a lot of young, a lot of old, they all average out to be right in the middle. Is there any data around that average? Well, let's say this is population. Any data around that average? No. Which is fine. The average actually doesn't even have to be a data point. 1, 1, 1, 1, 1, 10, 10, 10, 10, 10. The average is going to be way in the middle of 1 and 10. Or it's not going to be anywhere near like a data point. So I'd expect this standard deviation to be a little larger than normal, right? Because my data is all far away from the mean. Way up, way down. Here's the neat thing about standard deviation. There's this guy, I call him Chubby Dude sometimes, so if I say that, realize I'm talking about Chebyshev, obviously Russian, who discovered that the first piece of this is going to be pretty lame, to be completely honest. He said, if you step, and let's give ourselves some numbers here. Let's say the average is like 40. Just to give myself a number. And let's say the standard deviation is, what, Jeff? 10. Let's make it nice. All right. So if I take, let me see if you guys, I'm going to be using this kind of terminology and these types of symbols here in the near future a lot. So if I take one step up, that'll be mu plus 1 standard deviation. Let me just stop right there and let you absorb. If I take one step, and I often think of standard deviation as steps. If I take one step up, what number is that, of course? 50, because I start at 40 and I go up by one step of 10. That's 50. If I take one step down, what would it be in symbols? Mu minus 1 sigma. And of course, what is that as a number?
30.
30. And a quick word about that. The reason I call it steps, one thing about the standard deviation, has anybody ever been on the road and you go through a little town, you're on this road, you're going like 80 miles an hour, and suddenly the speed limit sign says 35 because you're going through one of these towns. If you blink, you miss it, right? So if you really wanted to investigate that town, wouldn't you take smaller steps? Because if you take too big of a step, you're through it, you haven't seen a damn thing, right? So if my data is really tight, I want to take really small steps to get around it. Because if my data is tight and I take a big-ass step, my data's gone. I just passed the whole damn thing. Whereas if it's really freaking spread out like Denver, if you ever been to Denver, it's like spread out, or even San Diego, then you want to take big steps to get the hell around the damn thing, right? So I often call standard deviation steps because they are that's a nice analogy. Did I catch any data by doing this? No. So within one standard deviation, how much data could there be?
0.
None. So what Chebyshev is saying is for any freaking distribution, any set of numbers you can imagine, this is where it gets a little bit more interesting. These 3 things he's going to say are true. He actually said a lot more than that, but we're only going to worry about the 3 of them. The first thing is kind of stupid. Within one standard deviation, there's at least how much? 0%. It's like, thanks, dude. You really took a chance there. It could be about 0 of it in there. Well, that's great. Thanks. Here's the funky thing. If I take, are you guys semi-cool with this so far? I want you to really understand, I just created one example. I could have made any damn example I wanted to, and what I'm about to say would be true. If I take one more step, now from my picture, what happens if I take one more step?
You get some data.
I get mu plus 2 sigma, which in this case is 60. One more step of 10, right? And mu minus 2 sigma, which is 20. Then I definitely am going to catch some data, right? Now, being completely honest, I totally made this up. How long is this? Is that really a step of 10? I'm just making all this shit up as I go along. So you could say, well, maybe it's really like this. Maybe I can pull this guy up here and pull that guy down there. Maybe that's really what it's more like. But then what would happen to the standard deviation? If you pull this down and pull that up, the standard deviation will get bigger. So as it's trying to escape, I'm stepping at it, I'm coming at it, right? And the data's like, oh shit. But the minute it moves, my steps get bigger, right? So that's what he realized. He says, no matter what your data looks like, within 2 standard deviations, there must be at least 75% of the data. If you really think about it, no matter what, you come up with a set of 100 numbers. And I'll calculate the mean and the average, and if I go out 2 steps up and down, I'll catch 75% of your data at least. I don't care how you freaking make your data set. I don't care. Use whatever numbers you want to. Use negative numbers. Use square root of pi. I don't care. Use billions and 2. I don't care. Bam, bam, I'll catch 75% of your data. I guarantee it, at least. That's kind of nifty. Possibly. All right. Some of you guys are still like, I don't know what the hell you're saying. I don't know if it's nifty. And then the last thing is within 3 standard deviations, at least 89%. Because if I go one more step down and one more step up, I'm going to catch even more data. Okay. So what that means is, coming back to our data. Because is our data necessarily truly normal? A truly normal distribution? Not necessarily, right? So I can't say it's some kind of distribution. Well, this works for any distribution. This here works for any distribution. So what did we figure out for men? We saw the mean was 69.9. And we saw the standard deviation was 3.123.
Yes.
So between what 2 heights would I be able to find at least 75% of all the heights in here for men? So between what 2 heights would I be able to find 75% at least of all the men's heights in here? So how do you set that up? I kind of drew a line here to maybe get us started. Right in the middle you should put the mean. Beautiful. The mean should go right in the middle. And then you start stepping up and down. Here's the mean. One step up would be what number?
79.9.
Careful now. One step. Now be careful. This standard deviation for my made-up thing was 10. This standard deviation for our true data that we had is 3.123.
Add it up.
So add it up, yeah. So you get
70.
73.023. So that's mu plus 1 standard deviation, right? And one step down would be that minus the standard deviation.
66.777.
Cool. That's mu minus 1 standard deviation. So you're going to see some problems in the book, and then of course we've got to take one more step here, but you're going to see some problems in the book where they say the average time is this and the standard deviation is this. Between what 2 times would you say 89% of the data? Well, you go, oh, that's 3 steps out, according to the chubby dude. So take 3 steps out and get those 2 numbers. Answer done, right? So you can always set up this number line right off the bat. Just set it up, just start going up, down, set it up, and now you can answer any damn question they throw at you. So one more step up would be
76.146.
76.146, and one more step down.
63.054.
63.054. Yeah, cool. So then between what 2 heights is 75%? Between about 63 inches and 76 inches roughly. Right, just rounding off a little bit. Between those 2 heights, I would find 75% of the men. in here? Period. Yes, sir.
63.654.
How come you get 65? I thought 63.6.
654 is it?
Yeah.
Oh yeah, that makes more sense. So let's say 63.7 roughly inches. Yes, ma'am.
63, not 65. You put on a
63, yeah. My 3 looks like something else. Yes, okay. Either a 5 or some other language. All right, how do we kind of get the idea there? So if they give you a problem, and this is kind of cool, if you calculate the mean for some set of data, and it works for sample data too, if you calculate the mean to be 28, and the standard deviation to be 2, you can, the very first thing you can do is start making this chart here. You can go up and down, one step, right? And one cool thing you can say, this is 0 away, this is 1 up, and this is 1 down. You guys see that? Mm-hmm. This is 0, this is 1 up, 1 down. 1 more up, 1 more down, right? 1 more up, 1 more down. And then you can answer if I say, what percentage of the data would you find between 24 and 32?
75%.
How much?
75%.
At least 75%. Beautiful. Okay. If you really think about it, that's crazy. I don't care what set of data. Find the mean, the standard deviation. You know these things for sure. That's kind of crazy. If you think about it, it's kind of cool. That's a lot of power to have with just 2 freaking numbers. So to get a little more specific, Chebyshev works for what kind of distribution? Any kind of distribution. What's a normal distribution look like again? Bell curve. I love it. And it's got a lot more restrictions. It's got to be biggest where?
In the middle.
In the middle. So I can't have one like I just did. So the rule for it, to be more specific for a bell-shaped curve, I can get much more exact rules for it. And they are the rules that are going to rule our life in Chapter 6 and beyond. Right? These rules I'm about to set up. So this is called the Empirical Rule. So this only works for normal distributions. I always sound drunk when I say distributions. So it's got to be a bell curve. And here I think I'm going to do it mostly visually, possibly here. All right, that's roughly bell-shaped. Yes, sir?
Would that apply for normal distribution for like a loose line?
No. Loosely normal is no good for this.
Okay.
Right? Then I can then say it's roughly this percentage, but it won't, the language will have to change, right? I can't say that it is this. So let me just go straight to the point here. Let's say this is the mean, whatever it is, and this is up 1 step and down 1 step. Is that okay? Up another step, down another step, up another step, down another step. Okay. How we doing? So what could this be? Couldn't this be 80 and the standard deviation could be 7 and then this would be 87? So doesn't this represent like all possibilities? The mean is itself. It's 0 away. This is 1 step away, whatever the hell that is. This is 1 step down, whatever the hell that is. Okay. Well, always hopeful. Here's what Empirical Rule says. It says within 1 standard deviation, you will catch 68% of the data. And it's actually 68.26 or something, but it's 68% of the data. We're going to stick with a nice whole number. So there is 68% in here. So if you know you're working with normal or close enough to normal data, you know exactly what percentage is within 1 step. Yes, ma'am? Cool. I can do that. Within, see, does this work? Within 2 steps, you catch 95% of the data. Now think about that for a minute. If I know it's normal, like heights actually are normally normal, then I know if I take 2 steps up and 2 steps down, I've caught like 95% of the people, right? So before I finish this out, think about how tall doors are, for example. How did they design that, or how wide airplane seats are, right? They take the average butt width, actually hip width, Right? And then they take the standard deviation and they say, what percentage of customers do we want to be upset at us that they can't fit in their seats? Right? You guys with me? And then that they can figure it out. If they're cool with like, what percentage would be up here? If this is 95%, let me see if you guys can get this. What is just up here? 2.5%. You guys with me? If this is 95%, how much is outside total? 5%. Just on that side is 2.5%. So if they're cool with 2.5% of their customers being upset at them, then they'll set the width to be there, whatever number that is. So I'll take the average hip width and add a couple of standard deviations to it and say, there's our seat. So now I can expect about 2.5% of the people to complain or to have to buy another seat or whatever. Do you guys see the immediate, you don't get this in a lot of math classes, but we have an immediate application of something we're doing right now, right? They do this. They do exactly this in everyday life. The last step here is one more step out to 3. Once you get out to 3, it's crazy. There's 99.7% of the data within 3 standard deviations. So we can see that, for example, with heights. The average men's height is like 5'9.5" or something. You don't get a lot of men that are freaking 8 feet tall. You don't get a lot of men that are, 2 feet tall. Most of us are here, fewer out here, even fewer out. You see how that kind of makes sense with what you see every day? And this is actually why it's a normal curve. What would you do if you saw this guy right there? What would you do if you just saw him walking down the street? That's the 8 foot tall dude. What would you do? You're not going to tell me you're just going to go, no, you're going to go, whoa. Right? Like when I saw Manute Bol. Anybody know Manute Bol? Used to be the Twin Towers on where was he at? Golden State and Nuggets too. So I saw him when I got off Southwestern Air. You can't miss him. He was like, I was like, whoa, this tall ass dude. So you're gonna, and that's why it's not normal. It's out of the ordinary when you see something out here or down there, right? Okay, cool. So you'll see problems just the same as I said before. They'll say this is a normal distribution with a mean of this and a standard deviation of that. You can make your same number line and then just look back at the empirical rule to tell what percentage is in there. Let me ask you this. What percentage is from 0 to 1?
68%.
I'm going to get you guys used to this notation. The percentage, or probability really, but let me just call it percentage right now, between 0 and 1, I'm getting a little ahead of myself, that's all right. Let's just say this, between 0 and 1 will definitely be, how related to 68%?
Yeah.
Cut in half, yeah, 34%. Because of the symmetry, right? The mean cuts it in half. Cool. So you will have some problems where you have to play around with the picture a little bit. You have to cut it in half or add it back together or get just on this side like we did up here, right? Just playing around with the numbers a little bit. Okay. Cool. I like it. So just to look at the homework real quick, they do give you lists of data, so you can put those in your calculators. I need you to copy your list down on your homework. If I don't see those, I'm going to make you redo it. So don't do all this work and then don't give me enough and you have to redo it. Copy your list down onto your homework page. This is the only time in this class you'll have to do that. So do it now. And then thank God you don't have to do it again later. I'm just going to make you suffer through this section. Okay. Cool. So I think I do want to do just a couple things out of 3-4, unless you guys have a question on something we just did. So what's Chebyshev for? Any distribution within one step there's 0% at least. Within 2 there's at least 75. Within 3 at least 89. Empirical, you know a lot more. So within 1 step up and down there's
68%.
within 2
95%.
within 3
97.9.
99.7. Cool. I like it. Yeah.
On the test, we need to copy down all our lists.
On the test, I'm just going to give you one problem like that. And you do have to give me the list and show me all your columns. Yeah, cool. But again, after that test, you'll never have to do that again. Not even on the final. So just go through it now. Let me see what you guys think about this. I'll start off with a nice example, which won't tell us what the formula is, and then I'll give you a harder example. Let's say the mean for something was 38, and the standard deviation, let's say, is 9. How many steps away is this? How many standard deviations does it take to get from here to there?
2.
How'd you figure that out?
Add 9.
Say again?
You could add 9 up.
Okay, 9 times 2, a couple steps. One step obviously isn't enough. So then you take one more step, you can see that's it, right? So the number of standard deviations away from the mean for 56 is 2. This is going to be a very important number to know, because that's going to tell me where I am in the rule here, right? If I know I'm 2 steps up and 2 steps down, I know where I am in the rule. So I've got to be able to calculate how far away I am. So what if I had this instead? What if I had a mean of 38 and the standard deviation is 9? How far away then does it take to get to 42? How many steps is 42 away? And I want to know exactly how many steps. I want to know exactly how many steps away it is. So if it's 3/10 of a step, I want to know 0.3, right?
2/3. 4 divided by 9.
Well, be careful now. You can't square root a fraction now.
What was the number?
So how far do you have to go?
What was the
How
number?
far do you have to go?
42.
From 38 to 42, how far do you have to go? 4. And how big is each step you take? 9 big. This sounds a little bit like doing class width. I've got to go 4. Every step I take is 9 big. So that's 4/9 of a step, isn't it? That's 4/9 of a step, a little less than half of a step up. If you do this in a calculator, you get 0.4 forever. Right? So that's, again, what does it tell you again? 4/9 is what? What is 4/9 exactly that we just did? The number of standard deviations from the mean to that data point. Keep saying that.
How
It
did
must
you
be
get
important.
4/9?
So this is the number of standard deviations. Put it over there too. Hold on. Away from the mean to 42. Let me give this to you guys.
No, I said, how did you get 4/9?
I'll show you. Let me put it up here. We had 38, 42. The mean here, the standard deviation was 9. So how many steps? If I take one step up, isn't that too many? Don't I go to 47? One step up. So it's less than one step. It's a partial, a ratio of a step. It's a part of a step. How much of a step is it? It's 4 out of 9. Right?
Yeah.
The distance I got to go divided by how big each step is. Cool. And actually, if you look back at the first one we did, how far do you have to go? 18 divided by 9, 2. 2 steps fit in there, right? Here, 4/9 of a step fit in there because this is smaller than one step. So this is what's called, and somebody, maybe you can give me the what formula did we actually just use then? We did 42 minus 38. The 38 is the mean. Cool? What's the 42? X. I love it. It's just some X. Just some data point. Divided by
9.
standard deviation. And 9, and for that case specifically, in general, standard deviation. That is officially called the z-score. And that will, again, the z-score will basically be our life once we get into Chapter 6 and beyond. It will rule everything. So what I like to say about z-score and standard deviation is kind of like the tick marks on the ruler. It tells me if I want to measure from here to the next town, would I use inches? No, my tick mark's going to be huge. I'm going to use miles maybe, right? Then I lay down my big-ass ruler between the two towns like I'm a god here. Bam. See how far apart these towns are. Or if I want to see how far apart these guys are from each other, I would use maybe actually inches. And then I lay my ruler down and take a measurement. So standard deviation are the tick marks. How far apart those are? The z-score is the actual measurement, right? Because the z-score tells me how far away I am from the middle. So I like that kind of visual. When you calculate standard deviation, you're setting up your ruler. And then when you see what a z-score is for a data point, you're laying your ruler down and saying, okay, how far away is it? Yeah.
What about going the other way? Do you use negative numbers or no?
Exactly. Cool. I didn't want to bring that in too early, but if I had a number down here, let's apply that formula directly now. If I have, let's say, a mean of 110, standard deviation is 22. What's the z-score for 68? What would that formula look like? What's your x in this case? 68. Don't put the big number first. You put the x first. 68 minus the mean, 110, divided by the standard deviation, 22. Yeah, it'll come out negative, right?
Negative
You'll get negative
149.
42 over 22.
So
Negative 1.9090.
1.9.
09.
So about negative 1.91. Is that cool? Okay. Yes, ma'am.
With the 68, you just make that up.
I totally made that up. Yeah. So say this is like IQ scores. The average IQ score is actually 100, but let's just pretend like it's some island somewhere it's 110. And I want to know, there's this guy who's 68. How bad off is he? He's almost 2 steps below the average. Right? Cool.
So it can be negative.
Definitely. The negative or the positive just tells you if it's above or below. So if I told you on your test, I say you got a negative 3 z-score in your test, did you do really well or really poorly? Freaking bad. You're 3 steps below the average. Kind of bad, right? You're way down all by yourself. That sucks. If I told you got a z-score of 2.7,
You did pretty good.
and what does that mean then? Exactly, what does a z-score 2.7 mean?
You did almost 3 steps above the...
Almost 3. So you're 2.7. Standard deviations above the mean. I love it. So I will have a certain question on every single test in here. I'm giving you this question. The question will be, what does the z-score tell you? And I have yet to get less than about 6 people get that wrong. It really makes me cry when I get in the 20s. But very simply, what does the z-score tell you? It tells you the number of standard deviations from the mean to a data point, right? Any variation of that. The z-score tells you the number of standard deviations from the mean to a data point. I love it. Now you can memorize that, that's fine. I'd rather you kind of be able to say it in your own words, but if you say it like that, I love it, right? Because it's so freaking important to know what that is. Yeah?
Now when we want to know the percentage that falls into range, so this kind of gives me the ratio.
No, but you got to be careful. I like that you said that. Right now, the only rule we have about percentage of data that's somewhere can only go by whole number steps, right? Within 1, within 2. We don't have, is this a linear thing? No. If I go further out, I'm getting less and less percentage here, right? So later in this course, we're going to have the empirical rule on steroids. We're going to have this chart showing to 2 decimal places all the freaking values from negative 3.5 up to positive 3.5. So if we have a problem like this, and we want to know what percentage of people have less than that IQ, we can just look that up in the chart. It'll tell me the percentage of people that would be below there. That's kind of crazy, right? Empirical rule does that for me, but only if I know it's a whole number. So I could round that to -2 and say it's about this, but I want to know exactly, yeah. Okay. Cool. So what I think I want to do is, so we got through z-score, so you can expect a z-score question from me, like on the practice test, number 5, obviously, number 2, stuff like that, right? You guys with me? What you won't see on the test, because I'm not going to be able to get through that today in 5 minutes, it's the end of section 3-4. Do you see number 1F? 1F. P40, what the hell is that? How many guys took an SAT test yet? Anybody taking their SAT? When you get your results back, don't you get a percentile, like you're in the 88th percentile or the 27th? Would you rather be in the 88th percentile or the 27th?
88.
What does that really mean? Did you make an 88 on the test?
No.
No.
What does it mean?
That's your
Score's higher than
I like it.
88%.
Your score was higher than 88% of everybody else who took that test on that day scored. It's a relative score, right? So if they happen to make a really hard SAT test, then you expect everybody's grade to drop, but your percentile would be the same. So the college wouldn't go, oh, you did that. No, they see the same number. That makes it fair. You guys kind of get what I'm saying? If they change a test and they're like, oh shit, we made it way hard, your percentile will say the same because everybody should do about the same worse, right? So that's what that is. It's a percentile. So we'll finish that up after the test. So homework through section 3.3 is due. I am warning you that I will have Z-score question on that, and that's from section 3.4, but section 3.4 homework is not due on the day of the test. Is that cool? Is that understood? Yes. I didn't get through anything last time because I have all the homework you turned in so far back on Monday.
Yeah.